Okay, in our last episode, we were finishing up on this, which hopefully you guys caught the other video on this. Okay, so now we're going to move on. Now we're going to move on to something called enthalpy. Now that's a pretty big idea in AP chemistry. You guys might remember, those of you had me for HChem, all right, I did mention about that, and it's abbreviated with the letter H. And it's a thermodynamic quantity equivalent to the total heat content of a system. So, I mean, if you think about it, you can look at it as the total energy that a system has and the work that it does. Okay? So it's a thermodynamic quantity equivalent to the total heat content of a system. It is equal to the internal energy of the system plus the product of pressure and volume. Or H is equal to E, meaning energy, plus PV, which is pressure times volume. Now that's the definition. Now if I went and changed it and said the definition version 2.0, enthalpy is the energy plus the work of the system. That's what it is. Now normally you're not going to see H by itself. Usually you're going to have that triangle that's there. Yeah, did you see that eyeball in the triangle thing? Okay. No, it's normally you'll see enthalpy with the H on it. Okay. You'll see the triangle in front of the H. So enthalpy is at constant pressure, and delta H is equal to delta E plus pressure times the change in volume. Now we can look at the heat at constant pressure. QP can be calculated from delta E is equal to QP plus the work, which is equal to QP minus the P delta V. Now, wait a minute. Why is the P delta V minus? Well, remember, it's being done outward from the system into the surroundings. So when we look at the heat at constant pressure, that's our change in energy plus the pressure times the change in volume, which is equal to delta H. You're not going to see QP necessarily that often. You're going to see delta H way more often. And that's the enthalpy. That's what you guys need to be familiar with. Okay? Now with that, we got to look at something called calorimetry. You guys have seen me demonstrate something along the lines of burning a Dorito chip and making the water heat up, and then we would measure the temperature change, and we could actually calculate how much energy was in that Dorito chip. Or I may have burned other things in the class. I don't remember, because I've done it so many times. But calorimetry is a way of measuring the heat. Now we can use what's called a calorimeter. Now there's two basic kinds. One is a constant pressure calorimeter called a coffee cup calorimeter. Pretty straightforward. And the other is called a bomb calorimeter. Now the heat capacity for a material, C, is calculated. This is a pretty important idea about this heat capacity. The C, that heat capacity, is the heat absorbed divided by the change in delta T, otherwise known as delta H. Wait, where did we see that delta H before? Here. Heat at constant pressure is equal to the energy plus P delta V. That's where you saw it before. So when we look at it, C, our heat capacity, is heat absorbed divided by the delta T, which is equal to delta H divided by delta T. So when we look at a specific heat capacity, we look at the heat capacity divided by its mass. Okay, that sounds like a lot of math. But we got to get to a point. And here it is. We got to look at molar heat capacity. If we're looking at how much heat is involved, the heat capacity per mole, that's a pretty important idea. The molar specific heat capacity is the amount of heat energy required to raise the temperature of 1 mole of a substance. Now you'd say, but wait a minute, I could have sworn I heard you say something about raising the temperature of 1 gram of a substance. That's true too. It depends on how much you're measuring. Are you looking at the molar heat capacity, or are you just looking at the heat capacity per gram? okay, or per kilogram. How are you going to know that? Well, usually when delta H is connected, okay, with delta H, it usually has to do with molar heat capacity. That's usually the case. Make a note of it, okay? So heat is equal to the specific heat times the mass times the change in temperature. That's using mass. Now we can also calculate heat using the molar heat times the number of moles times the delta T. Again, we're using moles here. Now when we look at a coffee cup calorimeter, which is this little gizmo right here, which looks like a simple coffee cup with some water and a thermometer in there. You're right. That's a very simple coffee cup calorimeter. Now the coffee cup, the idea behind it, it doesn't let heat out, okay? Tries to keep it in. So with the idea that if you heat the water, we can measure the change in temperature. That's why they call it the coffee cup calorimeter. Okay? So with that, a coffee cup calorimeter measures delta H. Wait, where is that delta H? That was the enthalpy over here, remember? Delta H is equal to the change in energy plus pressure times the change in volume. This is at constant pressure. If this is not at constant pressure, guess what? This isn't going to be true. So that's a pretty important thing. Remember, we're looking at what's happening with the energy. We're looking at here the idea of basic calorimetry, and now we can look at it here. So a coffee cup calorimeter measures delta H, an insulated cup full of water. The specific heat of water is 1 calorie per gram times degrees Celsius. Now there we're not looking at the number of moles. We're not. Okay, for in this case here, for basic calorimetry, okay, which you guys are going to have a chance to do, you will. Okay, no, you're not burning a Dorito chip on this one. You are going to be working with another kind of experiment on this. The specific heat of water is 1 calorie per gram times Celsius. The heat of reaction, looking at delta H, is equal to the specific heat times the mass times delta T. And then the next slide, there's a couple of problems. Okay, this looks like a pretty complicated formula here. Here's the thing. There's another way to look at this formula. And I've used this in HChem. I know I've used this in physics, and I know I've used this in AP Chem. You could look at that specific heat, put that as C. You have delta T, and you have mass, M for mass. And we can look at delta H as Q, the energy that's involved, the heat of reaction, if you will, the energy that's involved. Q equals mass times the specific heat times the change in temperature, otherwise known as Q equals mCAT. Yeah, Q equals mCAT. Pretty simple idea. And it's a useful formula, okay? Now keep in mind, guys, when you're doing your tests, okay, you have reference sheets that are going to be with you, okay, for every test, because those are the exact same 3 or 4 pages worth of reference sheets that you will have with you on the day of the exam, okay? So this formula, yeah, it's your friend. You should know it, okay? Q equals mCAT, where Q, you could look at the total heat, you could look at the total energy, okay, equals mass times the specific heat times the change in time. Not time, temperature. It's getting a little late for me, okay? All right, guys, that's it here for this particular section. So we've looked at enthalpy, we looked at the idea that it's delta H, okay? We looked at energy plus the pressure times the volume, okay? And with that, I'm going to stop here for this. Oh, we're going to work on the next problems. I should go and pop those out right here, okay? So this, ladies and gentlemen, is what you have to look forward to in our next session. So we're going to do a couple of examples shortly.